The last few lectures have been all about the wave function, psi. And since psi is such an important concept in quantum mechanics, really the first entire chapter of the textbook is devoted to the wave function and all of its various properties. Since we've reached the end of chapter 1 now is a good opportunity to go and review the key concepts of quantum mechanics, in particular the wave function and how it is related to the rest of quantum mechanics. The key concepts, as I stated them earlier, were operators, the Schrodinger equation, and the wave function. Operators are used in the Schrodinger equation and act on the wave function. Your friend and mine, psi. What we haven't really talked about a lot yet is how to determine the wave function, and the wave function is determined as solutions to the Schrodinger equation. That's what chapter 2 is all about, solving the Schrodinger equation for various circumstances. The key concepts that we've talked about so far, operators and the wave function, conspire together to give you observable quantities. Things like position or momentum, or say the kinetic energy of a particle. But they don't give us these properties with certainty. In particular, the wave function really only gives us probabilities. And these probabilities don't give us really any certainty about what will happen. Uncertainty is one of the key concepts that we have to work with in quantum mechanics. So let's take each of these concepts in turn and talk about them in a little more detail, since now we have some actual results that we can use, some mathematics. We can put more meat on this concept map than just simply the concept map. First, the wave function. The wave function, psi, does not tell us anything with certainty. And it's a good thing, too, because psi, as a function of position and time, is complex. It's not a real number. And it's hard to imagine what it would mean to actually observe a real number. So the wave function is already on somewhat suspect ground here. But it has a meaningful connection to probability distributions if we more or less define the squared modulus, the absolute magnitude of the wave function, to be equal to a probability distribution. And this is the probability distribution for what? Well, it's the probability distribution for outcomes of measurements of position, for instance. You can think about this as a probability distribution for where you're likely to find the particle should you go looking for it. This interpretation as a probability distribution requires the wave function to be normalized. Namely, that if I integrate the squared magnitude of the wave function over the entire space that I'm interested in, I have to get 1. This means that if I look hard enough for the particle everywhere, I have to find it somewhere. The probability distributions, as I mentioned earlier, don't tell you anything with certainty. In particular, there is a good deal of uncertainty, which we express as a standard deviation or a variance. For instance, if I'm interested in the standard deviation of the uncertainty, or standard deviation of the position, it's most easy to express as the variance, which is the square of the standard deviation. And the square of this standard deviation, or the variance, is equal to the expectation value of the square of the position minus the square of the expectation value of the position. And we'll talk about expectation values in a moment. Expectation values are calculated using expressions with operators that look a lot like these sorts of integrals. In fact, I can re-express this as the expectation of the square in terms of a probability distribution is just the x squared times multiplied by the probability distribution with respect to x, integrated over all space. This is the expectation of x squared. I can add to that, or subtract from that, the square of the expectation of x, which has a very similar form. And that gives us our variance. So our wave function, which is complex, gives us probability distributions, which can be used to calculate expectation values and uncertainties. This probabilistic interpretation of quantum mechanics gets us into some trouble pretty quickly. I'm going to move this up now, give myself some more space. Namely with the concept of wave function collapse. Now, collapse bothers a lot of people, and it should. This is really a philosophical problem with quantum mechanics, that we don't really have a good interpretation of what quantum mechanics really means for the nature of reality. But the collapse of the wave function is more or less a necessary consequence of the interpretation of the wave function as a probability distribution. If I have some states, some space, some coordinate system, and I plot on this coordinate system the squared magnitude of psi. This is related to our probability distribution with respect to position. If I then measure the position of the particle, what I'm going to get is, say I measure the particle to be here. Now, if I measure the position of the particle again immediately, I should get a number that's not too different than the number that I just got. And this is just sort of to make sure that if I repeat a measurement, it's consistent with itself, that I don't have particles jumping around truly randomly. If I know the position, I know the position. That's a reasonable assumption. What that means is that the new probability distribution for the position of the particle after the measurement is very sharply peaked about the position of the measurement. If this transition from a wave function, for instance, that has support here to a wave function that has no support here did not happen instantaneously, it's imaginable that if I tried to measure the particle's position twice in very rapid succession, that I would have one particle measured here and another particle measured here. Does that really mean I have one particle, or do I have two particles? These particles could be separated by quite a large distance in space, and my measurements could be not separated by very much in time, so I might be getting into problems with special relativity and the speed of light. And these sorts of considerations are what leads to the Copenhagen interpretation of quantum mechanics, which centers on this idea of wave functions as probability distributions and wave function collapse as part of the measurement process. Now, I mentioned operators in the context of expectation values. Operators are our second major concept in quantum mechanics. What about operators in the wave function? Well, operators, let's just write a general operator as q hat. Hats usually signify operators. Operators always act on something. You can never really have an operator in isolation. And what the operators act on is usually the wave function. We have a couple of operators that we've encountered, namely the position operator, x hat, which is defined as x times. And what's it multiplied by? Well, it's multiplied by the wave function. We also have the momentum operator, p hat, and that's equal to minus I h bar times the partial derivative with respect to x of what? Well, of the wave function. We also have the kinetic energy, which I'll write as ke hat. You could also write it as t hat. That operator is equal to minus h bar squared over 2m times the second derivative with respect to position of what? Well, of the wave function. And finally, we have h hat, the Hamiltonian, which is an expression of the total energy in the wave function. It's a combination of the kinetic energy operator here, which you can see, first of all, as p squared. We have a second derivative with respect to position and minus h bar squared. This is just p squared divided by 2m. P squared over 2m is a classical kinetic energy. The analogy is reasonably clear there. You add a potential energy term in here, and you get the Hamiltonian. Now, expectation values of operators like this are calculated as integrals. The expectation value of q, for instance, is the integral of psi star times q acting on psi over all space. This bears a striking resemblance to our expression, for instance, for the expectation of the position, which was the integral of just x times rho of x, where rho of x is now given by the absolute magnitude of psi squared, which is given by psi star times psi. Now, basically, the pattern here is you take your operator and you sandwich it between psi star and psi. And you can think about this position as being sandwiched between psi star and psi as well, because we're just multiplying by it. It doesn't really matter where I put it in the expression. The sandwich between psi star and psi of the operator is more significant when you have operators with derivatives in them. But I'm getting a little long-winded about this. Perhaps suffice it to say that operators in the wave function allow us to calculate meaningful physical quantities, like x, the expectation of position. This is more or less where we would expect to find the particle. Or the expectation of p, and I should be putting hats on these since technically they're operators. The expectation of p is more or less the expected value of the momentum, the sorts of momenta that the system can have. Or the expectation value of h, the typical energy the system has. And all of these are tied together in the context of uncertainty. For instance, if I wanted to calculate the uncertainty in the momentum, I can do that with the same sort of machinery we used when we were talking about probability, that I calculate the expectation of p squared and I subtract the expectation of p squared. So the expectation of the square minus the square of the expectations is directly related to the uncertainty. So that's a little bit about operators and a little bit about the wave function and a little bit about how they're used. Operators acting on the wave function calculating expectations in the context of the wave function being treated as a probability distribution. Now, where are we all going with this? We're going towards the Schrodinger equation. And the Schrodinger equation, to write it out, is I h bar partial derivative with respect to time of the wave function, and that's equal to minus h bar squared over 2m second partial derivative with respect to position of the wave function, plus some potential function of x, times the wave function. Now the wave function psi here, I've left it off, is a function of position and time. So this is really the granddaddy of them all. This is the equation that we will be working with throughout Chapter 2. We will be writing this equation for various scenarios and solving it, and describing the properties of the solutions. So hopefully now you have a reasonable understanding of the wave function and enough understanding of operators to understand what to do with the wave function. The sorts of questions you can ask of the wave function are things like, what sorts of energy does this system have? How big is the spread in momenta? Where am I likely to find the particle if I went looking for it? But all of that relies on having the wave function, and you get the wave function by solving the Schrodinger equation. So that's where we're going with this. And that's all of the material for Chapter 1. And without further ado, moving on to the next lecture, we'll start solving the Schrodinger equation. So far, operators and the wave function conspire together to give you observable quantities. Things like position or momentum, or say the kinetic energy of a particle. But they don't give is how to determine the wave function, and the wave function is determined as solutions to the Schrodinger equation. That's what Chapter 2 is all about, solving the Schrodinger equation for various circumstances. The key concepts that we've talked about now is a good opportunity to go and review the key concepts of quantum mechanics, in particular the wave function and how it is related to the rest of quantum mechanics. The key concepts, as I stated them earlier, were operators, the Schrodinger equation, and the wave function. Operators are used in... The last few lectures have been all about the wave function, psi. And since psi is such an important concept in quantum mechanics, really the first entire chapter of the textbook is devoted to the wave function and all of its various properties. Since we've reached the end of Chapter 1 now, the Schrodinger equation, and act on the wave function. Your friend and mine, psi. What we haven't really talked about a lot yet